Welcome to Innovate and React. This episode will be a bit different, not a discussion with an expert, rather an introduction to a new topic. In this case, hydrogen and energy. Hydrogen is always on my mind because of my job, so I thought why not also have this topic on my podcast. When I talk to people about the energy future, there's always the same debate coming up. We all want to tackle climate change, right? We want to keep growing our economies, improve our lives, but do it all with clean, renewable energy. And on paper, that sounds perfect. Solar panels getting cheaper every year, wind turbines sprouting left and right. But there's the thing that energy sources that rely on the weather and the sun, they are kind of moody. So we don't have the energy always when we need them. Think about it. The sun doesn't shine at night. The wind blows not on command. And yet we need 24/7 electricity. For example, for hospitals or just for our convenience. When we flip the switch, we expect the light to come on. Whether it's noon on a sunny day or midnight during a calm evening. This creates what we call the intermittency problem and is putting serious stress on our energy system. In fact, globally there are over 1,000 gigawatts of renewable projects stuck in the grid connection queues right now, which means that there are enough renewable energy projects in the pipeline. However, the electricity grid cannot handle it, and therefore these projects come to an halt. If the electricity grid becomes unstable, we become what we have seen in Portugal and Spain last month. That's like having a fleet of electric cars but no charging stations. The bottleneck isn't the generation, it's our grid's inability to absorb and distribute this fluctuating power efficiently and in the amounts we need at the specific times. So what do we need? We need flexibility, massive amounts of energy storage. And this is exactly where hydrogen comes into play, as the missing link in our clean energy equation. So why is hydrogen such a game changer? Unlike batteries that store electricity directly, hydrogen is what we call an energy carrier. It's like a chemical battery, so to say. We can store electrical energy as a molecule in the form of hydrogen over months, and we can transport it over continents, we can transport it wherever we want. So how does this flexibility help? It can balance the grid second to second because electrolyzers can be ramped up, ramped down pretty fast. So when there's suddenly bad weather, no sun at night, so as a quick reminder, the electrolysis splits water and takes about 1.5 volts to split the water, but the efficiency depends on the electrolyte. And this can be used in an alkaline solution, for example, or ion conductive polymer in the so-called PEM technology. Hydrogen can also be used as a backup when there is no wind and low sun. Hydrogen can also be used as a backup when there is no wind or sun. We can convert the hydrogen back into electricity by turbines, motors, or the most efficient one, fuel cells, where hydrogen is directly converted together with oxygen back into water, and that yields electricity. And then, finally, as I said, the seasonal storage, which is stockpiling the energy from the summer where we have loads of photovoltaic power and we can store that for the cold winter nights when we need energy. Here's how it works in practice. On a windy day, when their turbines are producing more than the grid can handle, we can divert this surplus electricity with electrolyzers, the devices that split water into hydrogen and oxygen, converting the excess renewable electricity into energy carrier as a molecule. When the wind dies down, we either burn that hydrogen in turbines or use it in the industry that can't easily be electrified, like steel making or fertilizer production, where we need the hydrogen as the molecule, as a reductive agent. The International Energy Agency calls this beneficial electrification, turning temporary energy into long-term solutions. But here's the thing. Hydrogen isn't just a backup plan. It's the bridge between sectors. The same hydrogen that stabilizes the grid today could fuel trucks tomorrow or heat homes in the next decade. There's versatility you can't get from a lithium-ion battery. You can use the hydrogen as a molecule where you need it in the chemical industry, or use it as an energy source. Depending on where it's needed the most, you can use it. So why do we not have hydrogen abundant everywhere when this is such a great idea? Well, hydrogen is used in the industry for quite some time, but there it's so-called gray hydrogen, produced from steam reforming. And steam reforming has a terrible climate impact because a lot of CO2 is produced by reforming methane with water to get all the hydrogen out of water and the methane to eventually get CO2. And that's a lot. So with the green hydrogen, which comes from electrolysis and renewable energy sources, we have a classic chicken and egg dilemma. Industries won't adopt hydrogen until it's cheap and abundant, but producers won't scale up until there's steady demand. In the end, it's a bankability problem that both sides basically cannot really rely on the others, especially when everyone thinks that in the future the prices will come down a lot. So let's break this down. The supply side, electrolyzers costs are dropping. Electrolyzer companies predict a reduction of the costs already, but even with cheaper tech, we need 100 plus gigawatts of annual production to meet the climate goals. Last year, we were not even at 8 gigawatts worldwide. On the demand side, industries like shipping and aviation are hesitant. Switching to hydrogen means redesigning not only the supply chain, but also the engines, retrofitting ports, building entirely new supply chains. And they won't move until they know hydrogen is coming for good. There's also another problem. When we can move the hydrogen through pipelines, we can transport it easily. But if we want to connect our energy demand to places in the world where we have the best conditions for renewable electricity, then pipelines are not longer viable. We need to somehow use ships or other forms of transportation. And here's where chemistry comes to the rescue. Instead of pure hydrogen, researchers are turning it into easier to handle chemicals like ammonia or methanol, so we can import these compounds much easier from other places in the world. For example, ammonia is already a commodity and there are lots of ships transporting it. Same for methanol. Think of it like packaging a fragile glassware in bubble wrap. It adds steps, but it makes the whole system more robust. So we convert hydrogen into other energy carriers. And let's now look at these solutions. Ammonia, for example, It stores 50% more hydrogen per volume than liquid hydrogen. Japan has already tested ammonia-powered ships, and Australia plans to export solar-made ammonia to Asia. Methanol, made by combining green hydrogen with captured CO2, companies like Carbon Recycling International are producing it in Iceland and using geothermal energy. Synthetic jet fuels also can be produced from hydrogen using the Fischer-Tropsch process. Scientists convert hydrogen and CO2 into synthesis gas and then into kerosene. Lufthansa has tested this in 2023, cutting soot emissions by 90% because this synthetic fuel burns much cleaner than the conventional fossil fuels. These carriers solve two problems at once. They are easier to transport and they tap into existing infrastructure. As I said, for ammonia there are already ships available, but they can also be used in the same tanks as propane. Well, synthetic air fuels work just like today's fuel. It's just a replacement and can be used in the aircraft engines right now. So the chemistry behind this is basically a reverse combustion. You turn water into hydrogen and oxygen and combine it with CO2, turn that into synthesis gas and water, and then turn the synthesis gas into liquid hydrocarbons, which is the fuel. When it comes to ammonia, we use the Haber-Bosch process. Nitrogen is combined with hydrogen to make ammonia. And this reaction needs high pressures from usually 250 to 350 bar and high heat for around 450 degrees Celsius. Not exactly energy efficient, but new catalysts like ruthenium-based structures are helping to bring the energy demand down. For methanol, we can directly use CO2 and hydrogen, which is technically also this reverse combustion, but we don't need the conversion step into synthesis gas first, which is a mixture of CO and hydrogen. By 2030, electrolyzer capacity could hit 520 gigawatts if all the projects stay on track. China is currently leading with about 70% of global installations. But in Europe and the US, the projects are also ramping up. So what are the key challenges? Water use is one problem, especially in dry areas. To produce 1 kilogram of hydrogen, we need about 9 liters of ultra-pure water. In drought-prone areas, this could strain the resources even more. On the other hand, if investments from Europe, for example, go to less developed countries, there are arguments that we could just oversize the water production to also provide water for the population in these countries. Another challenge is infrastructure. We desperately need hydrogen pipelines, storage caverns, and retrofitted terminals which can handle ammonia and liquid hydrogen. Because this only allows a market to come up where hydrogen is traded as a commodity. And then we will see this whole economy start, because then competition reduces the prices and the ramp up will finally work. Another thing is policy. Currently, the fossil alternatives to electrified options or hydrogen-based options are still too cheap. It is just cheaper to put the CO2 in the atmosphere and risk climate change instead of using the clean alternatives that we already have. Carbon pricing and green hydrogen mandates could break this chicken and egg cycle. When stakeholders are forced to use some percentages these green alternatives, the market ramp up can accelerate, and all this price decline for electrolyzers and other technologies will come, which then will make it more competitive to the fossil alternatives. So here's the bigger picture. Hydrogen isn't just about saving the planet, it's also about energy independence. Countries with abundant sun or solar could become the new oil giants without the geopolitical baggage. This is also for Germany, for example, a very interesting point, that we can diversify our energy imports over more partners, and we can also produce more of the energy ourselves. All of the mentioned technologies still have room for improvement, and this is what the next episodes will be about. Research on how to improve methanol synthesis, Fischer-Tropsch, ammonia synthesis. I will be talking to researchers in these fields, and with this episode I wanted to give a bit more background, because this is not just chemistry, this is also a lot of energy and energy systems. If you also would like to contribute to one of these episodes, let me know. You can contact me via contact@innovateandreact.com. And then thank you very much for listening. Until next time, keep innovating and stay curious.